Hello everyone, and today we are presenting the firmware supply chain security is broken, and most important part, how we can fix it. And I'm Alex Matrosov, and today we are here with Alex Ermolov, Kai Michalis, and Richard Hughes. Few words about the Binary. It is a startup from the Southern California where we focus it on firmware supply chain problems and how we can fix it with the help of modern artificial intelligence technologies and program analysis.
Hi, I'm Kai. I'm from Immune. We provide an attestation as a service platform and combine that with deep firmware analysis and monitoring.
And let's talk about complexity of the supply chain. And to be honest, we have a lot of parties involved, and the complexity of the supply chain and firmware and hardware side is just getting more complicated every year. It's not like we can fix problem with a single vendor. Usually it's many vendors involved and many parties. It's why always it's create significant delays on the patch delivery or fix delivery to end device. And the perfect example where basically we have a disclosure timeline, and usually it's actually take a while, 6 to 9 months, but also different parties is actually can introduce different problems. Hardware vendor can fail on the hardware security features configuration, and actually another part, it can be basically hardware device manufacturer can forget to disable write protection, or another one, it is firmware third-party developer introduce some SMM vulnerability, which is allows the attacker to escalate the privileges. So if you think about that, we have a distributed supply chain problems, which is not involved a single party. Of course, these failures can be combined in a perfect exploit to use for the attacker for the end customer. And one of the good examples about these problems, it is actually American Megatrends USBRT vulnerability, which has been found quite a while ago, but still it's getting discovered because it's open very complicated attack surface. And if we can see here how it's constantly get failed, and actually the same attack vector get fixed multiple times. And pretty recently, actually the last year, it's been fixed again. This year we have Asus Tech get fixed this issue again. And to be honest, we have a few disclosures ongoing where we rediscover the similar issue with another vendors. It's actually create very huge problem when we report in the firmware vulnerability, and fix takes around 6 to 9 months. But another problem, it is delivery this fix to end devices, endpoint devices.
So while we're at the topic of supply chain, let's talk about attacks on the supply chain specifically. So here's one from Asus. Attackers were able to get their certificate, sign their malware with the Asus certificate, then upload it back to their server and supply that to all their customers. Here's another one from SolarWinds. This was this year. Attackers were able to attack the SolarWinds network, got into the build server, and injected malware into the build process. This was later then signed by SolarWinds and pushed to their customers, which gives a good insight into how useful the secure boot mechanism is, where you just verify signatures. And if you look at our supply chain here, we have, for example, Acer that got hit by ransomware attack just this year. The attacker asked for $50 million. By the way, they also leaked all the internal information that they got using this ransomware attack. And then after Acer was asked about this attack, their response was pretty much, well, yeah, happens all the time. Most of the time we catch these guys. And if we find anything, we call the cops. And then something about how they try to improve every day. Here's another from Gigabyte. Also this year, they got hit by ransomware. The ransomware attacker leaked all the public information that they found there, but also passwords that presumably would allow an attacker to get into their system and, for example, backdoor all the firmware. We are lucky that these were just criminals that were after money and employed pretty loud and easy to detect attacks But it's easy to imagine that this would be as equally easy for a state-sponsored attacker to get in there and just backdoor the firmware and put more into all gigabyte systems, for example. So as a short recap, we have an extremely complex, intransparent supply chain, lots of third-party vendors. It's not really clear what goes into our firmware. There's no widespread use of things like software bill of materials. On top of that, we have extremely long disclosure timelines. So it becomes feasible for an attacker to, in case a new vulnerability is found in the upper parts of the supply chain and this information is leaked, the attacker still has time to inject, for example, another vulnerability downstream. And while the supply chain members are still arguing how to fix a specific problem, the attacker can already exploit systems that are out in the wild. We also have some misunderstanding there about security and support. A security problem is fixing a security problem is not a matter of whether the customer has an SLA with you or not. These have to be always fixed. And there seems to be a misunderstanding here in the firmware business. There also seems to be a limited ability to notify users. So before LVFS came onto the scene, there was pretty much no cohesive story for updating. So the vendor had to notify the users somehow. They had to pull the updates and then apply it to their systems. Thankfully, now with LVFS, we have the ability to push out updates as long as the vendor participates in the effort, and we don't have to notify every single customer. So how do we fix this problem, right? Our first idea is to come up with a vulnerability classification system that would give us a common vocabulary from the vendor side, from the security professionals, and also from the end users when we're talking about vulnerabilities and also how they are exploited. These vulnerability classifications already exist outside in the application world. For example, here's one. The idea is to pretty much enumerate all known vulnerabilities and give them a classification so we can figure out, okay, what mitigations work against what class of vulnerabilities. Here's another one. So these vulnerability classifications always create some kind of hierarchy where I can say, okay, I try to prevent a whole class of vulnerability using a specific technique. Okay, now comes the question, why do we need another one if you already have these? The problem with the vulnerability classification systems that are out there is that they're very focused on application level software. So we have, for example, the CWE, which has a specific entry for a specific problem with CSV files, or an entry for cross-site scripting. But there's not much in terms of firmware, for example. They have the missing ability to patch ROM code. I mean, that's a problem. But there's nothing, for example, for wrongly configured platform security features. Same with the attack framework. There's something about firmware corruption and the pre-OS boot attacks. If we then look at the mitigations, you see super generic mitigations. For example, here, they tell us to, well, enable some kind of signature verification in case it's supported. This is okay, but it doesn't talk about very specific features. It doesn't talk about the fact that many of these vulnerabilities can already be exploited before the signature verification phase. Another problem with CWE, for example, is that they also includes a classification of what an attacker has to be able to do in order to exploit something. And their classification just has 3 levels. 2 of them are network and 1 is local. And local includes both a physical attacker as well as somebody who has just shell access. And for application level software, this is probably okay. But in firmware terms, it's a gigantic difference whether an attacker is able to connect, for example, a Thunderbolt device onto your system or just have software access using SSH.
Yeah, thank you, Kai. And it's been a perfect introduction why we need to create another specification and classification for vulnerabilities based on an impact. And actually how this started quite a while ago, together with my book co-authors, Sergey Bratos, Eugene Rodionov, we created one vulnerability specification for targeting particularly UEFI firmware vulnerabilities based on the impact. And it's been good try. It's get very positive feedback from the industry. And we actually team up together with Kai, Richard, and Philip to create such of the new specification, which will be not only targeting UEFI firmware security risk, but also in general firmware security vulnerabilities. And we focus it on classification will be actually more generally based on the impact of actual vulnerability. And if you think on these two big classes like compromised supply chain and post-exploitation, it's actually exactly what's happening on current attack surface, right? So we have a lot of misconfigured vendors. We have a lot of vendors that actually not get fixed on some of the primitives. It's actually been fixed on other platforms, but not on the particular ones with vendors. Like as example, you have unauthenticated firmware update, and it's actually open the huge problems. And sometimes we think like BIOS lock enable is actually everywhere, right? So it's not even the mitigations, it's actually requirement to be present on all the platforms. But in reality, a lot of vendors forget to enable it. Some of the vendors just don't care and don't focus it on security at all. And we see this in the field a lot. And we create this specification to help the industry get patched and also prioritize the risks in the right way based on the impact to make sure you are not extending your attack surface on device security posture. Also, this actually very complicated graph, how we try to classify the issues and basically how this workflow works. We will have a workshop pretty soon and tomorrow, and actually this workshop will be focused on how we classify these issues, how we actually see the impact, and we will help you and walk through our approaches about these problems on the particular examples. So actually disclosing and getting fixed the vulnerability is one side of the problem. Another, it is deliver this patch at scale to many systems in the field. And to be honest, it's much more complicated problem to actually get fixed, developed, and shipped from the vendor, because we have very big diversity of different hardware vendors and hardware platforms in the field. And all these hardware vendors have their own timelines to actually make fix delivered. And perfect example of this diversity and supply chain failures, it is Intel BSSA DFT issue, where actually we already presented this year on Black Hat Vegas with Adam Zabrodsky and Alex Tiroshkin together. So basically we explained how this vulnerabilities work, but it's been very huge industry problem where actually not signed binary block can be loaded during platform initialization stage and can be controlled by the attacker to survive during other boot stages and deliver malicious payload to system management mode. And actually it is impacting a lot of different vendors, and not all the vendors present on this slide, it's much bigger impact. And all these vendors actually have their own patch cycles. All these vendors need to be aware about this problem as exists, and also plan this fix to be shipped on their platform. So the issue being on Intel reference code. So Intel need to be developed this fix, then this fix need to be shipped to the hardware vendors or American Megatrends independent BIOS developers, which is actually need to implement this fix in their framework, and then this framework gets shipped to device manufacturers and independent hardware developers, actually ODMs, and then they deliver the fix to their customers. And it's complicated delivery problem a lot, because all these stages have their own timelines. And basically, based on our personal statistics, after disclosing the issue can be rediscovered on other devices, even after 2 years, or like it's ridiculous timelines when one day became a 0-day for a while just because of this complicated supply chain. So we created also some approach with actually helping vendors to have a tool which is help them to identify vulnerable platforms in the field. And this tool called firmware hunt rules, where we use a semantic approach to actually create very specific rules for UEFI firmwares. It's much more precise and create less the false positives for compared to Yara. Also, it is more focused on code semantics from UEFI firmware specifics, which is actually create much more precise detections. On another side, the rules get more simplified and much easier to read. So actually, it is an example of BSSA detection with firmware hunt framework and UEFI R2 scanner. So you can actually get more details in our workshop how it works. And we also developed IDA Pro plugin to simplify development of firmware hunt rules. And you can see basically it's pretty easy. So you run the plugin, you try to create some notifications and actually annotations on what you wanted to use in the rule. And then basically you go which protocol you wanted to use, which NVRAM variable you wanted to use for detection. And then you can actually just highlight some code pattern to make this detection happens. And Richard, your turn.
So the LVFS is this software distribution sort of website essentially that allows vendors to distribute millions of firmwares to devices in the field. But if you step back a bit and think, what extra things can the LVFS do? If the simplest thing it can provide is a way for security researchers to say, I've got this rule, how many devices or how many vendors does it match? So if you're a security researcher, you can use the LVFS and you can scan all the public firmware. And I guess you could do the easiest thing to do would be to go to the vendor website and download all of the BIOSes for all their systems and then decompress them all into EFI binaries and then scan them all using UEFI-R2 or Yara manually. That's hundreds of gigabytes and it's going to take you literally days to decompress all those binaries. And so the LVFS has this interface where you can just write a UEFI-R2 rule, run it, and then 5 minutes later, it will give you the results back. So this is really useful. So we're using this at the moment with Vince, which is like a division of CERT, which is where we can say, okay, a researcher's found this vulnerability, let's say, for instance, for HP hardware, and we can find out which devices are affected, which lets them prioritize it between departments or groups. And we can also find, more interestingly, other vendors that are affected, where we might think that a vulnerability is Intel specific, but actually, sorry, HP specific, but it might be an Intel reference code issue, which is being reused by Dell and all the other OEMs as well. And so we've already used this quite effectively for one or two issues. And I think as we go forward, it's going to be used even more. So one thing the LVFS has done quite well for the last year or so is detect something called microcode downgrade. Now this is where a security team might ship an updated Intel microcode as part of a security update for a security issue. And that goes out to millions of users, that's great. And then the normal firmware team comes along with an enhancement update, which might add support for something or fix something else. And they upload to the LVFS. And they didn't include the fix from the previous security team. And this happens all the time. This has happened dozens and dozens of times between, I don't know, 4 or 5 different vendors. And the LVFS will say, hey, you've basically backed out this security fix. Are you sure you know what you're doing? Now, if we can do that for microcode downgrade, maybe we could do that for CVEs as well. Like Binali's been working quite a lot on doing things like control flow analysis. So if there's a security issue where, I don't know, a buffer check gets put in, so you check the length of a buffer, and that's just added into the existing code and the EFI binary is recompiled. Well, it's not like you're compiling these binaries on some random developer workstation. Typically, you're doing it with some VM in these tightly controlled conditions. And so the binary that comes out, it's actually very similar to the binary that they produced last time. And so with quite high confidence, you can create a UFR2 rule, which would detect this kind of control flow change. So that means that we could say, okay, sure, well, you fixed this bug 6 months ago, but you've reintroduced it when you added support for this new hardware. And that would be really good. And we're not far off that doing that now. So like the other thing we can do, we can sort of take this full circle. We've got the public vulnerabilities, which have already been patched by vendors. And we can run all of the existing UFR2 rules we used as part of the cert vince process. We can use those in the public LVFS and just say scan all firmware with these rules, which kind of catches the stuff we know about because we use that as part of the initial cert submission. But it also catches the new vendors that join the LVFS, and they say, hey, I've got this firmware I want to upload to Linux users, and they upload this firmware, and whoa, hang on a minute, we didn't know, but it's actually affecting by this CVE as well. Or if a vendor adds another type of device, like say if Intel, say if Lenovo ThinkStation joins, which might be it's the same Lenovo, but they might not have scanned the models before, and therefore triggering the CVE as well. So this is a really good way of kind of stopping the firmware going out to end users. We don't want users to have insecure firmware. We want the uploader to be aware of this as soon as possible.
Okay, shout out to the open source tooling that we talked about and that's out there. First, the Converged Security Suite. That's an open source test suite for your platform security features. So you can independently verify that the hardware you got was correctly and securely provisioned by the vendor. We of course have the firmware hunt and the UEFA tooling around that. Alex talked about that. This is super useful in order to run these standardized rule sets that you get against your firmware, right? So you can figure out, okay, are certain vulnerabilities in that firmware. Then we have the EFI Explorer plugin for IDA Pro, which allows you to deep dive into specific firmware, figure out what's happening there, write rule sets for firmware hunt, and figure out, are there any vulnerabilities? And of course, LVFS, which integrates that pretty nicely, so you can, as you heard, figure out, okay, are there other vendors that have these vulnerabilities there? So, most important, how to get involved. We need your help. So the Open Source Firmware Foundation is starting a firmware security work stream. We want to educate vendors using specification and guidelines on how to do secure firmware development, how to correctly take care of vulnerabilities, how to do incident response, how to do disclosure of these incidents in a fast but effective way. We need people who have the right knowledge and have the willing to commit the right amount of time that's necessary in order to do that. So we have some kind of discretion involved who gets in. But if you're interested, you can check out the link here. It's in the slides. There's a Google form that you can fill out, and we come back to you. And if you have our team assembled, and we are sure that there's not one vendor that's overly represented there, but have a good mix, then we start with our security work stream next year, and we'll develop specification on how to do effective firmware development.
Thank you very much, all. It's been great to be on the stage of Open Source Security Conference, and actually it's a very short talk, but we try to cover very important topics. Thank you very much. Really appreciate your time.